Hello everyone, my name is Andrew. Today we'll continue learning Python, and today I'll explain what is the speed of an algorithm and how do we measure it. So let's start. Once again, today we'll talk about the complexity, speed, quickness of an algorithm. So let's start with an algorithm. So what's that? An algorithm is a set of steps that you do in order to achieve some task, in order to get some result. And if you're talking about the code, anything can be an algorithm. A piece of code, a function, I don't know, maybe your program, your environment can be an algorithm, anything can be an algorithm, but typically it's something like a function. So a set of steps, so a step of instructions in our case that we execute in order to receive some result. So here I have a function called indexOf. It accepts container and find element. So basically it goes through each index in the container and checks if the value at that index is the same as find element. If that's the case, then we return the index. So basically it gives us the index of a value in the container. So if I have something like a list A, and then I print index of container from A and I don't know, let's go for 3, what's going to happen is that I'm going to receive 2, because, well, indices start from 0 and we go 0, 1, 2. Number 3 is on the second index, and we receive 2 as the result of index of function. But how do we measure if that algorithm is better than, for example, the same thing, which is a.index3? So a.index3 is basically the same algorithm, but it's written in Python. So it's a built-in algorithm. I do not need to write the function in order to call it. How do we measure the speed of indexOf versus a.index from 3? What's the difference? Which algorithm is better in our case? And what's better? Better is basically faster. So we want our algorithms to be faster, we want our results to be there. So if I can receive my result in 3 seconds, I want it in 3 seconds, not in 10 minutes or 10 hours. Because, yeah, if you have results ready, then your algorithm is better. So if the algorithm is faster, it's better. But how do we measure and how do we compare algorithms in IT? So what we can do is we can look at the code. So let's imagine that I have defined indexOf and indexOf2. Let's forget about a.index for now. So we have two functions, and what you can do at first is just look at the code. So for example, if I do something like for j in range 100, that's of course is really stupid. But if I do something like for I in range from a container, so I go through each index and then I go and make a loop that runs 100 times, and I just compare container and find element, I can literally see that indexOf2 is more complex than indexOf. Why is that? Because we run our if 100 times. So that if is run 100 times, but it doesn't really help the algorithm, because what we do is we say, okay, for I in range, so for some index, what you're going to do is run a loop that's going to run 100 times. So you're going to create a loop that runs 100 times, and then you're going to compare the same element on the same index to the same find element. So basically that loop is useless. And if I look at the code, I can analyze it and see that indexOf is better in that case. But of course, in indexOf2, for j in range is just an example. Of course, you're not going to see that in real programs. So the first thing that you can do is just look at the code, but it's not always that obvious. So yeah, we have 100 more steps on each iteration of the first cycle or the first loop. And yeah, of course, it's obvious here, but some cases are more complex. So what do we do if we want to check the speed of an algorithm? Well, the most obvious thing, maybe you thought about it already, is to just go and measure the time. So what we do is we import time library in Python, and then we say start time is time.monotonic. Basically, we get the current time. Then we say the same for end time, and we run our algorithm here. So print indexOf, for example, container A and value 3. And then we say print end time minus start time. So if you don't know, time is measured in integers or float values. So time is basically a number, and that number increments every second. So that number goes up and up and up every second. So what we're doing here is we're saying that our start time is some point in our timeline. So some integer, some value. Not an integer, but some value, some numerical value. Then we run our algorithm, and then we say end time is time monotonic, so the same point. But what's the idea here is that start time and end time have a difference. and the difference is the speed of an algorithm. So basically, if an algorithm takes 3 seconds, start time and end time are going to have a 3-second difference between them. And if I subtract one numerical value from another, I can see the difference. So I can see like 3 or 10 or I don't know, 60 seconds. So I can see the value of seconds if I subtract that. And let's run our code and we will see that 0, 0. So our algorithm is instant. We don't have any difference between start time and end time. But that's just because our list is too simple. So Python is really, really fast and my computer is really powerful in that case. Because I can easily, or my computer can easily run through 5 integers and compare them to 3. Because that's really easy, because my list is only 5 integers. But what we can do in order to achieve some time difference is we can do something like this. So I'm gonna put 10 for I in range 1000, or let's do 10,000. And then what I'm gonna do is a.append 3. So what I have here is I have a list of 10,000 tens. So 10 is repeated for 10,000 times. And then at the end of that list, I have a 3. And what I'm gonna do is search for that 3 in that whole list. But because the 3 is at the end of the list, so the 3 is the last number, because I append it at the end of the list after I add all the 10s. We're gonna spend some time looking through each 10 in that list of 10,000 elements. And then we're gonna go to 10,000 and the first element, and we're gonna see 3 as the result. So let's run our code and we will see that, okay, we still don't have any delay. Let's add another 0. Okay, now we have some delay. So when I have 100,000 elements in my list, I can see that my index of algorithm takes 0.01 second. So 1 microsecond or nanosecond. Let's add some more. So we have 1 million elements right now. And now we can see that we have 0.125 seconds. If I add even more elements, I can see that we have 1 second and 2 milliseconds. So that's better. Our algorithm index of takes 1 second for that search. Okay, so then what we should do is we just simply comment that out and say print index. And of course, let's write, so we have 1.2 seconds here, 1.2 seconds. And what I'm going to do is write index of 2. And I'm going to put the same parameters in there. So what I did is I first measured the time of index of function, and then I put index of 2 with the same parameters, the same inputs. And if I run it, you're going to see that our function is much slower. So it's very, very, very slow. As you can see, it's not even like 5 seconds, it's not even 6, not even 10 seconds. The program may take 1 minute, may take 2 minutes. So let's just wait until it completes. But while it's running, I'm going to tell you what the problem with that method is. So the problem is many computers, or all the computers, have different hardware. All the computers have different programs. All the computers have different memory allocations. So what do I mean by that? You can't really measure. Oh yeah, as you can see, the second algorithm takes 33 seconds. So that's really that's a lot. That's really a lot. And yeah, you can see that index of is better because it takes only 1.2 seconds, but index of 2 takes 33. But what is the problem with that method? What's the problem with measuring just the time? The problem is that every computer, as I said, has different hardware. So if I take my computer and Google servers, what's going to happen is that Google servers are more powerful. So if I run index of 2 on Google servers, it can finish in like 0.0001 seconds, because Google servers are very, very powerful. But if I run it on my computer or a very old machine, what's going to happen is that index of can finish in like 10 minutes, can finish in an hour, if the machine is old enough. So basically what you're experiencing is that different hardware can execute different algorithms with different time differences. So in our case, if I run index of, which is faster in that case, it's faster because we know that we have this unusable nested loop. I know that index of is faster, but if I run it on my computer or a very old computer, it's gonna show me some time. But if I run index of on a Google server or on a very powerful machine, it's gonna show me some other time difference. And that time difference in index of 2 can be faster than index of, because it depends on the hardware. It depends on what computer are we using. That's the first thing. The second thing is all the programs on that computer. So right now I have my PyCharm open, I have my OBS open, I have some other programs like Windows Defender, I have Chrome, I have Explorer, I have all those programs open. And each program can execute some different operations, can run some background tasks, can do some memory allocation, can get some CPU power, and so on. And with every program, with every command inside of every program, we can take different amounts of CPU and different amounts of memory. So basically what's going to happen, or what can happen, is that if you have two algorithms that are really close to each other, but still have a difference, is that when you run the first algorithm, one program can run a very slow background task that takes lots of CPU or lots of memory. And your first algorithm, which is better than the second algorithm, but they're really close again, so both algorithms are really close in their speed, but the first one is better. But if your system does something that limits your CPU power, or limits your memory power, or limits your RAM power, what's going to happen is that your better algorithm, your most simple algorithm, can run slower just because of the other programs that are running in your system. And you can't really avoid that, because each operating system has some programs that are required to be running, like, I don't know, Explorer in that case, or Bash in case of Linux, or some background services, something. And different programs can affect your computer and therefore affect the performance of different algorithms. And if your algorithms are really close to each other, so for example, we have 1.2 seconds here and 1.20003 seconds here. So the difference is very small. But if we look at the big values, if we look at, I don't know, 20 million elements, 20 or 200 million elements in a list, then the difference can be very large. That 0003 can go into 1 minute, can go into 2 minutes, can go into 10 minutes. And we want the fastest algorithm, because some applications require the fastest algorithm. And I mean, all of them require the fastest algorithm, but in some applications, it's really crucial to have the best algorithm possible. And that's why you can't really measure your time with just, or your algorithm complexity, your algorithm speed with just time, because of the hardware. So if you have different hardware, your algorithm can give false results, or your measurements can give false results. And if you have different programs running on the same computer, even if I use the same hardware, so even if I use two computers with the same hardware and run the programs at the same time, different programs and different services in those computers can interact with the CPU and therefore limit my algorithm's power. So that's it. If your algorithms are close enough, you will not find the difference, but there is a difference. So how do we go about that? We cannot really measure time, so what do we do? Well, the easiest way for us to measure the algorithm complexity or algorithm speed, you're going to know why I call it complexity a little bit later, is what we can do is count all the steps. So each algorithm has a command. So for example, for I in range when container, that's a command. For j in range, if container from I is find element. Container from I, that's a command. We need to get the value on that index. Return I, that's a command. And what we can do is approximate the number of steps that each algorithm takes. So basically, what we are going to do, we're going to go to index of, and we're going to say, okay, so let's count for I in range when container as one step. That's going to be one step. Then if container from I is find element, that's going to be another step. And the return is another step. And what we're going to do is count each step. So let's, for example, have a list. So I'm going to remove that, and I'm going to have something like 1, 2, 3, 4, 5. And let's say that I'm going to look for value. What's the value? The value is 3. I'm going to look for value 3 inside of my A list. So how many steps is it going to take? Well, first of all, we create our loop. One step. Then we check if our container is find element. The second step. Then we go to, well, 1. So our container from I, the first index, or index 0 gives us 1. That's not find element. 1 does not equal 3. So we go to our second value, to 2. Then we go to 3, and we finally return our 3. So it took us what? 1, 2, 3, 4, then 5, 6, 7 steps. 7 steps. So 3 steps, or so 1 step for the loop, for the loop with index 0, 1 step for if, so that's 2 steps, 1 step for the index 1, so for value 2, 1 step for 2 to 3 comparison. And then we go to 3. So 1 to 3, we have 4 steps, 6 or 4, 5, 6, 7. Okay, we counted 7 steps. So basically I go through each step in my algorithm, and how to count steps, I'm going to talk about that later. Just trust me. So I counted all the steps and I received 7. Then let's go to index of 2. So I'm gonna look for the same value, a, in the same list 3, so the inputs are the same, everything is the same. So value, inputs, all the same. But I'm gonna use index of 2. What's gonna happen? Well, algorithm is really, really close. So we have 4, then we have 4j. But 4j runs 100 times. So we already have something like, we have 7 multiplied by 100. Let's say that we have 700 steps in that index of 2 algorithm because of that 4j in range loop. And what do we see? We see that index of takes less steps than index of 2. And what can we conclude? We can conclude that if we want to execute index of 2, we're going to have to make 100 more steps on each iteration. Of course, it's not going to be 700, but it's going to be a much larger value. But just for comparison, let's say that index of 2 takes 700 steps to find 3. And what's going to happen is that index of 2 is going to execute more steps, and it doesn't really matter what hardware do we use, because the steps are going to be the same. Even if I run my program on a Google computer, I'm going to have 7 steps for index of, and 700 steps for index of 2, because that's just how the code works. We have the code and we run the steps. Their time does not matter, because if I run my index of on my own computer and index of 2 on Google's computer once again, then I'm going to receive 7 steps on my computer and 700 on Google's computer. But what's really, really important here is to understand that the more steps you have, the more complex algorithm you have, the more complex algorithm you operate. And we want to find the algorithm that has the least amount of steps. In our case, it's index of, so function index of. And we can conclude that index of is a better algorithm in that case. So index of is a better algorithm. We can either get rid of index of 2 or see if we can apply index of 2 in some other situation, because some algorithms are better with specific types of inputs. So yeah, I mean, the input can be different, but when you compare algorithms, the input should be the same. But some algorithms are good for some lists, some algorithms are good for other lists. So the input can change and the complexity and the speed of your algorithm can change as well. But when you compare, we use the same inputs. Well, we always use the same inputs. That's how it works. Okay, so now we know that index of is just better than index of 2. And one thing that is left for us to do is to somehow express that 7 as a mathematical function. Because sometimes your algorithm is really, really, really complicated. And imagine you're going to have something like 7 squared plus sqrt from, square from something, then some, I don't know, some sum. So you're going to have that e sign, you're going to have to sum something up, you're going to have to multiply something, and it's just really, really hard to take everything and just put it in a number. Of course, we can do that, but if we're talking about comparison, we don't really want a number. I don't want to know that my algorithm index of takes 7 steps. What I want to know is a mathematical function of how can I describe that index of in terms of steps. But I want a mathematical function for my analysis to compare index of and index of 2. So I want 2 mathematical functions, not 2 numbers, because it's just easier for mathematical functions to be compared. So what we do is we do not just count steps, but we get a mathematical function. We get some variables, we get the function. So what do? The function is called big O. So big O, what is that? Big O is the most amount of steps that your algorithm is going to make. So what does that mean? Imagine our algorithm A takes the most amount of steps. What is that? Or algorithm index of, sorry. What is that? If we want our algorithm to make the most amount of steps, we're going to have to look for number 5. Why is that? Because if we look for number 1, for example, what do? We initiate our loop, we compare our container I to find element, and we see that so if we look for number 1, we see that number 1, so container from index 0 is equal to find element. We can conclude that, okay, so the values are equal, we return I. So we return our index 0. But if you look at the number 5, what we're going to have to do is go through each value, go through 1, 2, 3, 4. And only after that we can go to container from I and return our find element. So return our index. Because 5 is the last number in our list. So we need to go through each number in order to get 5. And what can we conclude? We can conclude that in that algorithm, index of, the most amount of steps is that when we go through each value of our container. And we can also conclude that if we look at 5, it kind of represents the length of the container. So it represents the amount of numbers that we have. Because the max amount of steps is if we go through each number. So we go through 1, 2, 3, 4, 5. And if we do that, we go through kind of like the length of our container. So we go through each value, and each value is like what? 1, 2, 3, 4, 5. Well, we have 5 values inside of our container, and the length of that list is 5. So what we can do is say something like big O from n, where n is length from our list. So n is just a variable. That is the length of our list A. And of course we can write something like len from A, but typically when we work with big O, we want to represent everything in the variables. It's just easier for us to compare. And what I'm saying here, I'm saying that in the worst case scenario, big O is the worst case scenario of a function. We're going to have to make n steps. Of course, it's not true, because we're going to have more steps, a lot more steps. So we're going to have to initiate our cycle, we're going to have to create our range, we're going to have to get the length of our container, get the container from index. But what's really important is that we can see that typically we're going to have to make O from n steps. It's an approximation. Once again, it's not like a real value of steps, real amount of steps. Okay, then let's go to index of 2. What we can see here is we can see that we go through each value and we do it 100 times. So each value is 100 times. What we can conclude? We can conclude that our big O is going to be 100n, because we go through each value 100 times. And of course, n is len from A, once again. So that's for index of, and that's for index of 2. And we can see here that n is clearly less than, or clearly smaller than 100n. So we can conclude that n is smaller than 100n. We can see that that's just math. So we can see that easy. No numbers, just variables. And what we can conclude is that index of is better in the worst case scenario. So index of is better because we make less amount of steps in the worst case scenario. We don't want to look at the middle. We don't want to look at the first scenario. We want to look at the worst possible case scenario with big O. Big O is the most amount of steps. So the worst scenario. Because if you do the most amount of steps in your algorithm, the most amount of steps possible, that's the worst scenario, because you're going to spend more time doing those steps. And here we're saying that in order for us to go through each value in index of, we're going to make n steps. So we're going to go through each value of our list. We're going to go through length of our list. But in index of 2, we're going to have to make 100n steps. So that's a lot. And you can see that n is smaller than 100n, so we can conclude that our index of is faster. Once again, my name is Andrew. Thank you for watching, and bye-bye.